Transformers are devices that allow us to change voltages, AC voltages, from one level to another, or they can be used to isolate one voltage from another. And they operate on the principle of mutual inductance. So what we have basically are two coils of wire. So here we have one coil of wire, and we have the second coil of wire, and they're separated. These are literally coils of wire. They're inductors. They're insulated wire wrapped around a core many times. And what we learned earlier in the course is that if we have current flowing through a conductor, so if we have current flowing through this conductor, a magnetic field is created. Now we have this coil of wire, and we learned earlier that current, especially AC current flowing through a coil of wire, creates a large magnetic field. Now, a magnetic field, if it's close to a coil of wire, then we learned earlier that a voltage is induced on that coil of wire. So what we have is, on the primary side of the transformer, that's where the input voltage is applied. That causes a current to flow through the wire, through the coil. That coil has a magnetic field generated around it. This magnetic field on the primary side induces a voltage on the secondary side. That's mutual inductance. Now the levels of the voltages on the primary side and the secondary side, we can affect if the voltage on the primary side is stepped up or stepped down on the secondary side based on the number of turns of wire on each of the coils. Basically, it's the ratio of turns, primary turns, versus the number of turns on the secondary side. And that again determines if it's a step up transformer, a step down transformer, or if it's a 1-to-1 ratio, if there's literally the same number of wraps of wire on the primary and the secondary side, then that transformer is said to be an isolating or an isolation transformer. And that's where the voltage on the secondary side is literally isolated from the voltage on the primary side. So now that we know some of the basics of transformers, let's dig into a little bit of math. To do that, let's define a few things. We know that there are coils of wire on the primary side and on the secondary side. Coils of wire are literally wires wrapped around something, and we're going to define the number of turns of wire in the primary coil. N stands for number, and P stands for primary. So N sub P is the number of turns of wire in the primary coil. The number of turns in the secondary coil, N sub S, the voltage applied to the primary coil. Again, that's the applied voltage. That's the input voltage. So E is for voltage and P is for primary. And we have E sub S. That's the voltage that's induced onto the secondary coil. And that brings us to our first formula. N sub P, or the number of turns of wire on the primary, divided by N sub S, the number of turns on the secondary, equals the voltage applied to the primary divided by the voltage induced onto the secondary. So in other words, the ratio of turns equals the ratio of voltage. So let's say that we have N sub P, the number of turns on the primary, let's just say it's 500 turns. And on the secondary, we have fewer turns. We have 100 turns. And let's say we apply a voltage of 25 volts. So we have 25 volts AC applied. We have 500 turns on the primary. We have 100 turns on the secondary. We want to know what is the voltage at the secondary. We use this formula, and if we do the algebra, I'm not going to go through it step by step here, we end up with secondary voltage equals primary voltage times the number of turns on the primary, the number of turns on the secondary, my mistake, divided by the number of turns on the primary. And if we do this math with these inputs, we get the secondary voltage of 5 volts. So we have 25 volts coming in, we have 5 volts coming out. That means this transformer is a step-down transformer. One of the big things to remember, one of the big things to know about transformers is that power in equals power out. So power at the primary side equals power at the secondary side. So to explain that, let's define a few things. So I sub P, or I is for current, P is for primary. I sub P is the current flowing through the primary coil. I sub S, that's the current flowing through the secondary coil. And we already learned that E sub P is the voltage applied at the primary, and E sub S is the voltage induced at the secondary. And that brings us to our next equation. The ratio of primary current to secondary current equals the ratio of the secondary voltage over the primary voltage. Now let's take a step back. A few weeks ago, or certainly in DC fundamentals, you learned the power formula, and that is power equals voltage times current. And I mentioned earlier that power in equals power out. So knowing that power equals voltage times current, primary voltage times primary current equals secondary voltage times secondary current. And this formula actually shows that. So let's do an example. Let's say we have a load connected to the secondary. The load runs on 120 volts, so E sub S, secondary voltage, is 120 volts. And let's say that that load is drawing 10 amps of current. And let's say our primary voltage, that's the voltage applied, is 240 volts. So we want to know what is the current flowing through the primary. We know the voltage at the primary is 240 volts. We know the voltage at the secondary is 120 volts. We know the current flowing through the secondary is 10 amps. So what is the primary current? And again, I'm not going to do the algebra step by step here, but it works out that the primary current equals the secondary current times the secondary voltage divided by the primary voltage. And if we do this math with these inputs here, we end up with 5 amps at the primary. So 5 amps here at the primary. And finally, we're going to talk about transformer efficiencies. We now know that power in equals power out. That's only true in an ideal world. And of course, we know that conductors of wire have some internal resistance. So no transformer is ideal. So we need to be able to figure out the efficiency of a transformer. And that gives a formula. The efficiency of the transformer equals the power at the secondary, that's this value here, divided by the power at the primary. And we need to multiply that by 100. And I'll explain that in just a second. So let's say we have a load that is drawing 1,110 watts of power. And to deliver that 1,110 watts of power, the primary is supplying 1,200 watts of power. So plugging that into this formula here, we have 1,110 watts at the secondary. We have 1,200 watts at the primary. And I'm just going to ignore this times 100 just for a second. And that gives us 0.925. Efficiency, transformer efficiency, however, is always measured in percentage. So to convert the 0.925 into a percentage, that's the multiplied by 100, and so that yields 92.5% efficient transformer.